or I should say not property, but any properties are there. I'll find this property with respect to discrete time system. The first property is very important one, which is symmetry property. This symmetry property helps in solving, helps in simplifying the equation in the formula for the Fourier transform. Okay. Now we know the formula of Fourier transform is okay. This is the analysis equation, and this is the synthesis equation. Now if we assume that our signal xn is a complex valued and x of omega is also a complex valued, then I can write xn something like x of real part of n plus j times x of imaginary part of n. Okay. Similarly, I can write x of omega is x of real part of and j imaginary part of x of omega. Okay. Now e to the power minus j omega can be written as cos omega minus j sin omega. Now substituting 1, let this be 2, let this be 3. Substituting 1 and 3 in analysis equation. We get x of omega is equal to x r of n plus j x I of n summation whole multiplied by cos omega n minus j sin omega n. Okay. Now we can multiply the terms and separating the real imaginary part, I will get summation xr of n cos omega n plus xi of n sin omega n. This is the real part plus summation of j times the summation of x r of n sin omega n. This is minus plus xi of n cos omega n. Okay. This will be the imaginary. So x of omega, if I separate the real part and imaginary part, I can write x of real part of capital X of omega is equal to summation n tending to minus infinity to infinity x r of n cos omega n plus xi of n sin omega n, and the imaginary term will be minus n tending to minus infinity to infinity x r of n sin omega n minus xi of n cos omega n. This is okay. So these are the two expressions for the real part and imaginary part of the Fourier transform. I'll write those equations for real part of Fourier transform and imaginary part once again. Let this be equation number 1. Let this be equation number 2. Okay. So similarly I can write the equation xr of n from the synthesis equation 1 upon 2 pi integral 2 pi xr of omega cos omega n minus xi of omega sin omega n whole d omega. Imaginary part of the signal Sn is 1 by 2 pi integral of 2 pi xr of omega sin omega n plus xi of omega cos omega n. Okay. Now take the case. Case 1. If xn is real signal, okay, then what will happen? xrn equal to xn, xin equal to 0. Then I can write my xr of omega equal to summation n tending to minus infinity to infinity x of n cos omega n. Okay. And xi of omega I can write as minus n tending to minus infinity to infinity xn sin omega n. Okay. From this equation A and B, we can conclude that xr of omega is equal to xr of minus omega, that is E1. Xi of omega equal to minus times xi of minus omega, that is odd. Thus, if xn is real, its spectrum possesses which symmetry it is? Hermitian symmetry or conjugate symmetric. Okay. Next we will see case 2. If xn is real and even. In this case, if xn is real and even, then x of n cos omega n and xi of omega equal to 0. Thus, spectrum is contains only real part. Imaginary terms cancel in this. Okay. You can write only real term. Another case, third case, xn is real and odd. In this case, xr of omega is equal to 0 and x of I omega equal to minus 2 times summation n equal to 1 to infinity xn sin omega n. Thus, spectrum possess only imaginary value. Okay. So when signal is real and odd, spectrum is completely imaginary. We will take another case, case 4, in which xn is purely imaginary. Okay. Means xr of n equal to 0 and xn equal to j xin. So substituting this xn in the original equation of xr of omega and xi of omega, I will get xr of omega equal to n tending to minus infinity to infinity xi of n sin omega n. Xi of omega is equal to summation n tending to minus infinity to infinity xi of n cos omega n. So this is odd and this is even. We can say by this x of omega is conjugate antisymmetric. Okay. So depending on the signal x real or even, real and odd or purely imaginary, there can be case for purely imaginary and even and purely imaginary and odd. Okay. In such cases, a signal we can find that x of omega for purely imaginary and even, it x of omega is purely imaginary. For purely imaginary and odd, this is xn. This is xn. X of omega is purely real. Okay. So these are the points which we have to remember in the symmetry property of the Fourier transform. So in summary, I can write here xn, I'll write here x of omega. Real, it is conjugate symmetric. Xn is imaginary, it is conjugate antisymmetric. real and even will give real. Real and odd will make x of omega as imaginary. Imaginary and even will make x of omega imaginary only. Imaginary and odd xn will make x of omega as real. Okay, so 6 different type of signals and there are 6 corresponding x of omega. This thing should be remembered. This can come as a question in GATE exam. So these were the symmetry properties related with the Fourier transform. Next property is, among the general property, is linearity. Linearity states that if x1n is having Fourier transform as x1 omega and x2n is having Fourier transform as x2 omega, then ax1n plus b x2n gives me Fourier transform a x1 omega plus b x2 omega. Okay, this is the linearity property. Third one will be time shifting. Shift in time will not affect the magnitude spectra. It will only affect the phase spectra. Suppose if I have some sequence xn having Fourier transform x of omega, then x of n minus k will have Fourier transform e to the power minus j omega k x of omega. Thus we can see magnitude of this term is x of omega only. Okay, but phase has changed. Phase has changed. Initially phase for this is x of omega, then phase for this will become x of omega minus omega k. That's it. Okay, only the phase changes, magnitude spectrum will remain same. Next is time reversal. Reversing an input sequence will result a reversal in frequency domain also. If xn is having Fourier transform as x of omega, then x of minus n will have Fourier transform of x of minus omega. Okay. Again here phase is not magnitude spectrum is not changing, only phase is changing. Okay. Magnitude spectrum means unchanged. Phase spectrum undergoes change in sign. Okay. Convolution property. Convolution of two time domain sequence, if x1n is having Fourier transform as x1 omega, x2n is having Fourier transform x2 omega, then x1n convolve with x2n goes to multiplication in frequency domain. Okay, so this is the convolution theorem. This theorem sometimes helps in finding the convolution of two time domain sequence, because in frequency domain they become to multiplication. Multiplication is the easier process than convolution, because only multiplication is done there, but in convolution both multiplication as well as addition both are required. 6 says frequency shifting. Earlier we have shifted the time, now we will see the shift in frequency domain and how the time domain signal will affect. Then e to the power j omega naught n multiplied by xn will result in a frequency shift of x omega minus omega naught. Okay, this frequency shift principle helps in modulation theorem. Okay, next is differentiation in frequency domain. We cannot differentiate in time because time is discretized, okay, but we can differentiate in frequency domain because frequency is continuous for discrete time non-periodic signals. So if I have xn having Fourier transform of x of omega, then j times d of x of omega by d omega gives me n xn. Okay, so multiplication of n in xn will take place if I differentiate the time domain expression. How I achieve this expression? We know that x of omega is summation n tending to minus infinity to infinity x of n e to the power minus j omega n. So d by d omega of x omega is nothing but d by d omega of this expression. Now in this expression, the omega related term is only this. So if I differentiate this term, I will get minus j xn into n e to the power minus j omega n. Thus I can write here minus j d by d omega x of omega is equal to summation n tending to minus infinity to infinity n dot xn e to the power minus j omega n. Thus this term become a nxn. Okay. So this completes few properties of the Fourier transform. Okay. Next we will do certain problems which will relate to the Fourier transform and the topic which we have studied till now. Okay. So there will be lot number of problems, and those problems have already appeared in GATE exam. Some problems have appeared and some may not have appeared, but those kind of problems are likely to come, or the similar type of problems are supposed to